Hello and welcome to this week's video from Chemistry Unit 4, the periodic table. My name is Mr. Clee and this video is all about the Group 1 elements and flame testing. The aim of this video is that by the end of watching it you should be able to describe the reactions of Group 1 elements with water. You should be able to explain why they've got similarities, and you should also be able to explain the trend in the reactions with water. Firstly, Group 1, the left hand group of the periodic table. All of these are metals. They all have one electron in their outer shell. That's where the similar properties come from. The other name that they're given, other than Group 1 metals, is the alkali metals. This is because when they react with water, they all form alkalis. They form lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on. The reactivity depends on whereabouts in the group they are located. Firstly, because of their reactivity, all of the metals are stored in oil. This is to keep the oxygen in the air away from them so that they don't oxidize because of their high reactivity. Incidentally, this slide also shows one other feature of these metals, and it also shows the low density of lithium that you can see here floating in the oil. Sodium and potassium also have low density, but they are slightly higher than the oil that they're stored in, although less than water. You can almost think of these reactions as a little bit like a displacement reaction. The metals involved are more reactive than hydrogen in the water, so they almost displace one of the hydrogen ions. This means that when you get a metal, any of these metals reacted with water, you always form hydrogen gas and you always form a metal hydroxide. The general equation is metal plus water gives you metal hydroxide and hydrogen. You can substitute the name of any of the metals in this and the equation will be correct. Same goes for the symbol equation. M here is M for metal. You can substitute the symbol for any of the alkali metals in place of M and the symbol equation will work and will be balanced. So you could have, if you take potassium, you would have 2K plus H2O gives you 2KOH plus H2. It's perfectly balanced and accurate. So here's lithium. When lithium reacts with water, it keeps its shape, it fizzes around slowly, and it doesn't ignite. You can see the hydrogen gas being given off in the reaction here, but it has kept its shape, so there's not, although exothermic, it's not terribly exothermic. This will come in useful later. This is lithium's electronic structure, with 3 electrons, 1 in its outer shell. Moving on to sodium. Sodium has 11 electrons, 1 in its outer shell, so it has 3 occupied electron shells. This is the sodium metal. When it reacts, it is so exothermic that the metal actually melts and it turns into a little ball floating around on top of the water. It does state in the picture that universal indicator has been added to the water, which turns it purple. This is not universal indicator. It is an indicator that shows that an alkali is produced, and it is sodium hydroxide. The gas being produced, which is not that visible in this picture, is hydrogen. And thirdly, potassium. Potassium, you can see in the picture, has ignited. You can also see the wisps of hydrogen gas that have been produced. This is being carried out in a much more smaller container because it's a much more dangerous reaction. It's more vigorous, a lot more heat given off, faster rate of reaction. You can see here in potassium's electron structure, potassium has 19 electrons arranged in 4 shells with 1 in their outer shell. So moving down the group, all 3 metals float. There's always hydrogen produced, the metals gets pushed around on the surface. The rate of reaction is such that out of these 3, potassium wins, most reactive, sodium is second, and lithium is third. If you went further down the group to cesium and rubidium and francium, although francium is radioactive and doesn't really exist, the reactivity would get more and more and more. The reason for this is all to do with the distance between the positive nucleus and the electron that's being lost. The greater the distance between the positive nucleus and the electron that's being lost, the weaker the attractive force between the two of them. So the more easily they're lost. Potassium, its electron is being lost from the 4th shell, therefore it is more reactive than sodium, which has been lost from the 3rd shell, and lithium, which has been lost from the 2nd shell. If you were to go further down the table, when you get electrons lost from the 5th and 6th shell, they would be even more easily lost and therefore even more reactive. Two other patterns in the table. The first one here shows density. As you go down the periodic table, the metals become more dense, but they're all very light. The first three floating in water because the density is less than 1. In the second graph you can see melting point. Lithium has the highest melting point, and the melting point gets lower and lower and lower. Cesium would probably melt in your hand. However, you wouldn't want to put it in your hand because it would react with the sweat on your hand. So to summarise the alkali metals, the group 1 elements, reactivity increases as you go down. We always get a metal hydroxide and hydrogen gas. We explain similarities by the fact that one electron and one electron only is being lost from the outer shell, so it's very easy to do so. And we explain the differences because of the distance away from the positive nucleus that the electron is being lost from. Right, on to flame testing, the second part of this video. This gives you a simple method for how to carry out a flame test. Essentially what you have to do, you clean a nichrome wire. Nichrome is used because it's very unreactive. The way you do that is using hydrochloric acid because that reacts with any salts that might be left on it. Put a small sample on the end of the nichrome wire, hold it in the Bunsen burner flame just at the very edge, and the flame will change colour. This is where the metal ions are giving out light. Different colour is given off by different metals, and you can analyse the metals present by that colour. Three you need to be aware of are the same three that you saw in the alkali metals. Here is lithium, giving off a bright red flame. And finally, here is the lilac of potassium. It also burns when you put it into water, so you should be familiar with that colour. Finally, higher level stuff. The reason why. When you heat these metal compounds, the metal ions that are contained within them vaporise. They absorb heat energy. The electrons that are in their energy shells jump up to a more energised state. When these electrons jump up to a more energised state, they have to then come back down again to where they originally came from. When they come back down, that energy is given out as light energy. Depending on how far they fall when they drop back down, the amount of light energy that's given out is different. Therefore, every single metal gives out a slightly different amount of energy at a slightly different wavelength, looks a slightly different colour. So, in summary, we do flame test by putting a small amount of compound into a lit flame and observing the colour change. Lithium gives out red light, sodium orange, and potassium lilac, and the light is given out when energised electrons drop back down to their normal energy level, giving out the excess energy as coloured light. Thank you very much for watching. My name is Mr. Clee. If you've got any questions about this video or any others in the series, please see myself or any of your science teachers.